If you have watched all the video series up to this point, you know about the normal distribution, and you know that the z-distribution is another name for the standard normal distribution. Now I want to teach you about another very important distribution in statistics. It is called the t-distribution. In order to learn about the t-distribution, we have to first learn about the standard error of the mean. The standard error of a statistic is an estimate of the standard deviation of the statistic. So, the standard error of the mean is one example of standard error because we're talking about the standard error of a statistic, namely the mean. We find the standard error of the mean by taking the standard deviation of the sample and dividing it by the square root of the sample size. Here's the formula for the standard deviation of the mean. But if we don't know the standard deviation of the population, and we seldom know that, then we're going to need to estimate that standard deviation with the standard deviation of the sample. If we divide the standard deviation of the sample by the square root of n, that provides for us an estimate of the standard deviation of the mean. And to distinguish between the two, we call that estimate the standard error of the mean. From here, we can build up to the t-statistic. Draw a simple random sample of size n from the population. Suppose the population mean and standard deviation are both unknown. Quite frankly, I think it's rather peculiar to say that we do not know the mean of the population, but we do know the standard deviation of the population. It's almost always the case that we know neither of these. Dividing the deviation from the mean by the standard error produces a t-statistic. A z-statistic for the sampling distribution of the mean is the sample mean minus the population mean divided by the standard deviation of the population divided by the square root of n. But a t-statistic replaces the standard deviation of the mean with the standard error of the mean in the denominator of the formula. Now a t-statistic follows a t-distribution. T-distributions are bell-shaped, just like normal distributions, but they have heavier tails than the normal distribution. Here's a picture of a normal distribution, and here's a picture of a t-distribution. Notice that there are fewer units in the middle of the t-distribution than in the normal distribution because more of those units appear on the outside tails. That is, we have heavier tails in the t-distribution than in the normal distribution. A specific t-distribution is identified by the degrees of freedom. If you have watched past videos, you should know what degrees of freedom are, but let me go ahead and remind you anyway. Degrees of freedom refer to the number of items that are free to vary. In statistics, this is the number of values that provide new information. So in statistics, when we are calculating an average, we don't always divide by n, the sample size. We divide instead by the number of new pieces of information that we have when we calculate the statistic. For example, for standard deviation, in order to calculate the standard deviation, you must already have calculated the mean. Well, the degrees of freedom when you calculate the mean are indeed n, because every single score can be a different score. None of the scores are constrained when you calculate the mean, so we divide the sum of scores by n. When we calculate the standard deviation, we already have the mean. So let's suppose, for instance, that we have 3 scores and we know the mean is 5. How many scores are free to vary for y? Well, if we know the first one is 3 and the next one is 8, we know the average of all 3 scores has to equal 5, therefore the next score has to be 4. There were only 2 unique pieces of information here. So there are 2 degrees of freedom. Just like there are many normal distributions, there are many t-distributions, and they're identified by their degrees of freedom. This is a picture of a t-distribution with 2 degrees of freedom. Here's another picture showing the normal distribution, a t-distribution with 2 degrees of freedom in red, and a t-distribution with 5 degrees of freedom in blue. The larger the degrees of freedom, the lighter the tails of the distribution, and the closer the distribution is to normal. Let me add to the picture a third t-distribution, this one with degrees of freedom of 30. Notice that this green t-distribution is almost right on top of the black curve, which represents the normal distribution. The bigger the sample size, and therefore the more degrees of freedom, the closer the t-distribution will resemble the normal distribution. What are the implications for this? Well, let's go back to just comparing a single t-distribution with a normal distribution. If I calculate critical values for the normal distribution, wanting a 95% confidence interval, those critical values will both be near 2, plus and minus 2. That encompasses 95% of the normal distribution. But in order to encompass 95% of the t-distribution, we're going to have to put the critical values further out. That is, the critical values will be a larger positive and a smaller negative value. If you think about that in terms of margin of error, that will increase the margin of error and therefore increase the width of the confidence interval. Confidence intervals based on the z or standard normal distribution require knowing the population standard deviation. Confidence intervals based on the t-distribution only require estimating the standard deviation. So that is what we're going to end up doing most of the time because we don't know the population standard deviation. But there's a consequence to this. Confidence intervals based on the z-distribution where we have more knowledge are narrower than those based on the t-distribution where we're giving up some knowledge and we're needing to estimate the standard deviation. The good news is that the difference between z-based and t-based confidence intervals decreases as the sample size increases. Why? Because when the sample size increases, the degrees of freedom increase, and as degrees of freedom increase, the t-distribution looks more and more like a normal distribution. So the critical values are going to start getting closer to those of a normal distribution, and therefore the margin of error will also be similar to what we would get using a z-based confidence interval. In the next video, I'm going to show you how to create confidence intervals using the sample standard deviation and a t-distribution.